Okay guys, in this video we are going to talk about some more concepts within the valence bond theory approach to molecular electronic structure. This video is going to focus on hybridized atomic orbitals, which is used to explain molecular geometry. Recall from the previous chapter that we looked at all sorts of different molecular geometries, linear, trigonal, planar, tetrahedral, all those different geometries that we looked at. The goal of this video is to explain where those geometries come from. Why do molecules adopt those particular geometries? If we were to look at the main idea of the valence bond theory, which says that the bonds and the bond directions involve maximal atomic overlap between two atomic orbitals, we would wind up with all chemical bonds being either 90 degrees or 180 degrees. Let me explain that. So consider a molecule like water, okay? So H2O. So let this dot here represent the oxygen atom, and what we're showing here is a couple of the p orbitals on oxygen, and then these dots here, these represent the hydrogen atoms, and then the sphere, that represents the 1s orbital on each hydrogen atom. And so the idea here is that the bonds that form in water would involve the 1s orbitals on the hydrogen atoms and the 2s orbitals on the oxygen. And you can see that because the px and the py orbitals are 90 degrees relative to one another, we would expect that the bonding in water would also involve a 90-degree bond angle. But of course we know that that's not true from what we've studied previously, and it's also not true experimentally. The bond angle in water is not 90 degrees. So, this suggests that there's something wrong with the valence bond theory, or something not complete about it, at the very least. The same thing is true for carbon. If you consider an atomic orbital diagram for carbon, and I'm going to just make one really quickly here, if we look at the valence electrons for carbon, I guess that would be a 2s, and then we've got the 3 2p's. Carbon has 4 valence electrons, and so this is the orbital diagram for a carbon atom. If you need to form a chemical bond involving half-filled atomic orbitals with carbon, it suggests that carbon would only form 2 chemical bonds. However, carbon typically forms 4 bonds. And so this idea here isn't consistent with what we know experimentally, right? And so this is what the valence bond theory would predict, that carbon would only have two chemical bonds. It's not correct in terms of what's known about the chemistry of carbon. So there's something not quite right about the valence bond theory as we presented it so far. We need to adjust the valence bond theory in order to be consistent with what's known experimentally. And so that's where this idea of hybrid atomic orbitals comes from. So within valence bond theory, we need to allow our atomic orbitals to mix together. That is, we are going to form hybridized atomic orbitals. And what we're going to find is that these will indeed produce the correct molecular shapes that we've learned about in the previous chapter. And so we can take carbon as an example. In fact, we'll be using carbon in many of the graphics that I show you. We are going to take the valence orbitals on carbon, so the 2s and the 2p orbitals, and we're going to combine them in different ways. Keep in mind that these orbitals, they're really waves, and you can add and subtract waves in different ways from one another. And so this is going to create constructive and destructive interference in different regions of space around the atom. And what we're going to find is that the orbitals that we form, these so-called hybrid orbitals, they are going to have the correct geometry that we would expect based upon the VSEPR model that we've looked at before. Okay? And so hybridized atomic orbitals within the valence bond theory reproduce the VSEPR molecular geometries. One example at the bottom, and we'll look at some graphics related to this as well. If you combine the 2s orbital on carbon and the 3 2p orbitals on carbon, that is going to allow you to construct 4 new equivalent hybrid atomic orbitals. So I'm combining 4 atomic orbitals that we've already looked at, the 2s and the 3 2p's. I'm going to combine those waves. Those 4 waves are going to be combined to make 4 new waves. And they're all going to be equivalent to one another. And we are going to call them sp³ hybrids. That means that you've mixed 1 s orbital and 3 p orbitals to make a new set of orbitals that we call the sp³ hybrid orbitals. And it turns out that these 4 equivalent sp³ hybrid orbitals, they form a little tetrahedron. Okay? And so that's how you can take atomic orbitals that meet at only 90 and 180 degrees. You can combine them in different ways to get all sorts of geometries. And the tetrahedron geometry is one of them. So what this table does is it takes the VSEPR shapes that we've already learned about, and then it tells you which hybridization of atomic orbitals will reproduce that shape. Okay? So a linear geometry can be reproduced from an sp-hybridization. That is, you combine an s orbital with 1 p orbital, and that makes 2 equivalent sp hybrids. Okay? One of the sp hybrids points in this direction, the other sp hybrid points in that direction. And then these 2 unique atomic orbitals can then overlap with the atomic orbitals from another atom to give you the covalent bond. If you were to combine an s orbital and 2 p orbitals, you will wind up with a trigonal planar structure. So you have 3 atomic orbitals going in, an s and 2 p orbitals, and you get 3 hybrid orbitals coming out, and they each point to the corner of an equilateral triangle. Okay? And so that's where we get the trigonal planar geometry from. I've already discussed the sp³. 4 orbitals are combined, an s orbital and 3 p orbitals, and you get 4 new hybridized atomic orbitals coming out, and they each point to the corner of a tetrahedral shape. If you start adding in some d orbitals, so if you combine an s orbital, 3 p orbitals, and a d orbital, this gives rise to the trigonal bipyramidal shape. Okay? So notice you're combining 5 atomic orbitals. You get 5 hybridized atomic orbitals coming out. And they point, one of them points this way, another one that way, a third one points this way, and then you have the 2 axial ones that point up and down, above and below the trigonal plane. sp³d², you're combining 6 atomic orbitals, you get 6 hybrid orbitals coming out, and they point to the corners of this octahedral shape. Okay, so we need to know now, in addition to the VSEPR geometries, you now need to know which hybridization corresponds to which VSEPR geometry. What I'm going to be showing you next are some graphics related to these different types of hybridization. So what I'm going to be illustrating now is how these sp hybrids are constructed in a graphical way. And we'll also talk a little bit about the energetics of the situation as well. So what we've got here, this is 2 distinct pictures of orbitals. So in both cases, the nucleus is the same, right? So the two origins, those are actually the same. And on the picture on the left, we're looking at the s orbital. On the picture on the right, we're looking at the p orbital. Well, when you put these two waves on top of one another, you can add them or subtract them. Okay? If you add them together, it's going to produce this hybrid orbital. Okay? You see that it has a large lobe that points along the x-axis. If you subtract this orbital from that orbital, right, you can constructively or destructively add the waves together. If you subtract this wave function from that one, you're going to get this hybrid orbital, which is similar in shape, but it's pointing along the opposite direction. Right? It's pointing in the negative x direction. So two atomic orbitals go in, and you get two unique hybrid orbitals coming out. And each of these hybrid atomic orbitals can participate in bonding. And so we're going to be looking at a beryllium atom. Okay, so this is the atomic energy level diagram for beryllium. Beryllium has two valence electrons, and so they'll make their way into the 2s atomic orbital, and these are the unoccupied 2p orbitals. Now what we're going to do is to hybridize the atomic orbitals. So we're going to construct an sp hybridization, so we'll combine the s orbital and one of the 2p orbitals. That's going to make these new sp hybrids, and they have a bit higher energy than the 2s orbital and a bit lower energy than the 2p orbital. The 2p orbitals that we did not use, they remain unhybridized. So they're still there, they just don't have any electrons in them. The two electrons that were in the 2s orbital, one of them will go into the first sp, the other one will go into the other sp. In a sense, this is consistent with Hund's rules, where you keep the electrons maximally unpaired for as long as you can. And so now each of these sp orbitals, these guys, they each have one electron, and they can share it now with another atom. For example, a hydrogen atom that has one electron as well. Okay, so this is how the linear Vesper geometry comes about. We imagine that it comes about through this sp hybridization. Well, in the next slide here, we're attempting to visualize the sp² hybridization. So here we have three pictures, same atom, right? So the same atomic center. We're going to look at its 2s orbital and then two of its p orbitals. Okay, one's pointing along x, the other is pointing along y. There are three ways in which you can combine these orbitals, okay, to make three equivalent sp² hybrids. One of them points, unfortunately, they did not do justice to the geometry here in this diagram. They should have made the sp² hybrids. They should point to the corners of a triangle, and so they've attempted to do that here. They have not done a very good job in these two panels up here, whereas one points along x, the other one points along negative x, and this one points along y. That's not exactly the correct geometry. But if we look on the next slide, here we're looking at a top-down view of the three sp² hybrids, and we see that they've drawn it correctly with the proper geometry. And so here's just some molecular examples of that. Boron trihydride, for example, has a trigonal planar geometry. Each of these species do as well. Here in ethylene, there's a trigonal planar structure about this carbon, and then there's also a trigonal planar structure about that carbon. Well, here's what, here we're going to be doing the boron trihydride as an example. So we'll look at boron. Here's the atomic energy level diagram for boron. Boron has three valence electrons. Two of them are in the 2s and one of them is in the 2p. What we're going to do is we'll take the 2s, and now we're going to take two of those 2p atomic orbitals, and we're going to combine them in different ways to make the three equivalent sp² hybrid orbitals. The remaining p orbital is unhybridized and is unchanged, and it remains unoccupied. the 3 valence electrons now will occupy the 3 equivalent sp² hybrids, and they will remain maximally unpaired. So here we've drawn them all spin up. Now each of these electrons are occupying an orbital that points to the corner of a equilateral triangle. And so what you can do is then bring in a hydrogen atom. Each hydrogen atom that you bring in has a 1s orbital with 1 electron in it. And so those are the electrons that are going to be shared, on this corner of the equilateral triangle. All right, so you can imagine bringing in 3 electrons in these positions associated with the hydrogen atoms to form the 3 covalent bonds with good overlap, good atomic overlap between the sp² hybrid and the 1s orbital on the hydrogen atom. This diagram is illustrating the construction of sp³ hybrids. So here we're going to take a 2s orbital and all 3p orbitals. Now we're combining 4 atomic orbitals. The number of orbitals that go in equals the number of orbitals that come out. So if you combine 4 atomic orbitals, you're going to have 4 hybridized atomic orbitals coming out. And for these combinations, we are going to get sp³ hybrids that point to the corners of a tetrahedron structure. Here's another example of that. Here we're going to be looking at methane and ethane. Here is the atomic orbital diagram for an isolated carbon atom. It has 4 valence electrons. 2 of them occupy the 2s and the other 2 are in the 2p. We see that they're maximally unpaired. What we do to make the sp³ hybrids is we combine all 4 atomic orbitals in different ways to make 4 equivalent sp³ hybrids. And the 4 valence electrons that we had will then remain maximally unpaired. These guys point to the corners of a tetrahedron structure, if we look kind of like this here. And then for methane, each of these electrons can be paired up with an electron from a separate hydrogen atom. For the case of ethane, what we have here is we have 2 carbon atoms that have this sp³ hybridization. And 3 of the sp³ hybrids on each carbon will form an overlap with hydrogen atoms. That's why we have 6 hydrogen atoms here in ethane. The remaining 2 sp³ hybrids, 1 on each atom, can then overlap with each other to form a single bond between the 2 carbons. And so that's the structure that's being drawn over here. We have, for this carbon, there are 3 sigma bonds between carbon and hydrogens. There's 1 sigma bond with another carbon atom, and then the other carbon atom also has 3 sigma bonds with its 3 hydrogen atoms. Okay, so this is the valence bond picture of bonding within ethane. Each of these atomic overlaps gives rise to a chemical bond that we represent in the Lewis structure. And for this case, they're all sigma type. Right? If you look down the bond axis, you'll see that there's this circular or cylindrical symmetry to the bond. Here we have some diagrams illustrating the sp³-D and sp³-D2 hybrids. I won't go into too much detail here, but just to remind you that these are the hybridizations for trigonal bipyramidal, and then the sp³-D2, that is the hybridization for the octahedral shape. What we'll do now is we will look at several molecules and identify their hybridizations. Okay, so if you're able to do the VSEPR geometries for these molecules, then you should be able to just now tack onto it what would be the hybridization. Okay, so let's consider the boron trifluoride. Boron trifluoride is a well-known exception to the octet rule. It's an electron deficient species. Okay, so around boron we are going to have 3 electron pairs. Okay, this is going to be a trigonal planar geometry, and the hybridization for trigonal planar is sp². For H2O, this is the Lewis structure, right? It's a tetrahedron Vesper shape. Like, that's the parent Vesper geometry. But because two of the electron pairs are lone pairs, we say that it's the bent structure or the angular structure. Okay, so that's the molecular geometry, but the parent Vesper structure is tetrahedron, and so we would classify it as sp3. Same thing for ammonia. Here is the Lewis structure for ammonia. Okay, the parent Vesper geometry is tetrahedral. Because one of the electron pairs is a lone pair, this is the trigonal pyramidal structure. But the Vesper geometry is the one that we associate with the hybridization, and so it is also sp3 hybridized. The xenon tetrafluoride. I'm going to go ahead and take us through it just so I don't get the wrong Vesper structure. So we've got 8 plus 4 times 7. 36 electrons. We'll draw xenon here in the middle, put our fluorines around. We'll form our covalent bonds there, so that's 2, 4, 6, 8. So that's going to take us down to 28 electrons. And then each of these fluorine atoms gets 6. So 6 times 4, 24, leaving us with 4 more electrons to fill in. So 1, 2, 1, 2. We see that we've got 1, 2, 3, 4, 5, 6 electron pairs around the species. The parent Vesper geometry is the octahedron structure. Because two of the electron pairs are lone pairs, we would call this the square planar geometry. But the hybridization is based on the octahedral. So this would be sp3d2. For the phosphorus pentachloride, we've looked at this guy before. It's a hypervalent species as well. And, you know, the Lewis structure is going to be like this. I won't draw the lone pairs around the chlorines, but they're there. Each chlorine has an octet. And so the Vesper geometry here is the trigonal bipyramidal structure. And that's what the geometry is as well, since there's no lone pairs here. This is the sp²-D hybridization. Here we're being asked to look at the hybridization here in 2 molecules, urea and this would be acetic acid. So let's go ahead and do that. So we've got like so. Here's the Lewis structure, that you could come up with. And they want us to say, okay, what's the hybridization about each nitrogen? Well, we see that there's 1, 2, 3, 4 electron pairs around each one. So the parent Vesper shape around each one is the tetrahedron structure. And so that means that each nitrogen atom has an sp3 hybridization. So that's for the nitrogens. What about for the carbon? For the carbon, we've got 3 pairs. Okay, and so for the carbon, it would be, we'll talk about multiple bonds in the next video, but it turns out that that's going to be the trigonal planar structure. And then we would call it sp2 hybridized about the carbon. For the acetic acid structure, this is the Lewis structure you get. Okay. Tetrahedron structure here, so this is sp3. This one, sp2. For the oxygen, we call it sp3. Count up the bonding pair, the electron pairs, 1, 2, 3, 4. Okay, so that's tetrahedral, sp3 hybridization. For the carbon here, 1, 2, 3. Trigonal planar geometry, we associate that with sp2. Like I said, we'll talk about multiple bonds in the next video. And then about this oxygen, 1, 2, 3, 4 electron pairs. The parent Vesper structure is tetrahedron, and so it would be sp3. You might call the local geometry a bent structure. In any case, we need to be able to identify the hybridization for different molecular geometry types. Okay, and so I'm going to go ahead and stop this video here, and we'll pick up with the multiple bonds in the next one.